Thank you so much for inviting, and I'd like to express my utmost gratitude to James and Jay, as well as Dennis, for this incredible intercontinental convergence of engineering and science. So I'd like to, now you can relax. There will be no deep mechanistic data, but beautiful photos. Well, our research was inspired by this disease entity, left ventricular non-compassionate cardiomyopathy. Yesterday, our incredible graduate student was talking about congenital heart disease. This is one of the disease entities, and whereby this non-compacted trabecular muscle ridges could give rise to cardiomyopathy, heart failure, and arrhythmiogenic outcome. Well, so to study this model in a setting of epigenetic and genetic modification, we resorted to zebrafish model. And shown here is the zebrafish model, and showing this stage at which this endocardial trabeculation takes place. And so the question is, well, you probably remember zebrafish contains two chambers, the atrium and highly trabeculated ventricle, but similar to human being, the ECG pattern is typical for P-wave, QRS, and T, and as demonstrated by investigator at Children's Hospital. And in 2010, Ken at Duke further illustrated this capacity for this amputated heart to undergo regeneration in 60 days. So by 60 days, one can experience morphologic regeneration. But in our case, we'd like to study this electrical mechanical coupling in the setting of this regeneration. By using flexible electronics, now we can have a zebrafish carrying this device so that we can study this endocardial depolarization, repolarization phenomena as demonstrated by this changing QT interval from this QT prolongation in response to injury, followed by gradual normalization in the setting of tissue regeneration. Well, but the next question is how we can visualize this structural and functional processes. Shown here is the cartoon illustrating how laser light can penetrate into our biological tissue, but however, there's a limitation as to how deep this photon can penetrate, up to 1 millimeters. This is the so-called microscopic region or ballistic region, whereby most of us have been conducting research using confocal microscopy or light microscopy. However, to further penetrate deeper into this diffusive region, this is the region whereby CT scan and other imaging modality become useful to overcome this light scattering. So this mean-free pathway is actually a function of this light scattering. So the advance of light sheet microscopy in parallel with the current chemical clearing methods provide the basis to overcome this deep penetration for better resolution. So this is the cartoon illustrating the challenges with this diffusion region, whereby this light is shining the heart, but however, this zigzag mean-free pathway opaque the possibility to visualize the entire heart. In contrast, while performing confocal microscopy, one can remove and perform stitching so that that free pathway can become possible if you will perform surgical dissection and to expose the surface area. Well, the idea of imaging the entire heart without dissection is by using this optical clearance, as elegantly demonstrated by previous speaker, including Shang Wu. And so we have multiple generation of chemical clarity. So by clearing this diffusive region, now this mean-free pathway provides deep tissue penetration for visualization. And on the horizon is this photoacoustic approach by including presence of ultrasound to further delineate. But in this talk, I will focus on these optical approaches to provide deep light penetration. So the first part we'll be sharing with you, because a lot of people in this audience have been working with light sheet fluorescent microscopy. So we'll share with you our home-built dual illumination and detection system, followed by deep learning approaches to address big data and other imaging modality. This technology provides a basis to visualize cardiomorphogenesis and cardiomechanics. So light sheet fluorescent microscopy, or the so-called selective plane illumination microscopy, and can be visualized in this very unique optical pathway. Shown right here is the specimen. This laser blade will be illuminating the specimen. This could be a live zebrafish, and followed by this optical detection system. So this orthogonal pathway provides a basis to image objects without slicing or stitching. And then this multiple light sources through this optical component and could be detected through CMOS camera. So this idea was actually theoretically possible a century ago, but not until the advent of CMOS camera could we perform detection and acquiring data over 100 frames per second. So this optical pathway illustrating this fundamental basis whereby this fish could be visualized or any object through this optical pathway. So further expansion to demonstrate this possibility. And so this video illustrates this concept of this laser blade that could be slicing through this embryo. So within 30 seconds, data acquisition could be accomplished, followed by data reconstruction to give rise this type of scenario where you can visualize dynamic cardiac contraction in 2D, or visualize this three-dimensional structure. And I'll go over this further because you can appreciate this poorly defined anatomy, rendering difficulty for structure and function analysis. However, the ability to image live fish over time provide a basis to study trabeculation. Shown right here is the endocardium at 50 hours after fertilization in the presence of hemodynamic shear forces. And at 60 hours, one can appreciate the presence of endovascular trabeculation. So by 70 hours after fertilization, this ubiquitous endovascular ridges can form a unique pattern. However, as I shown before, data acquisition is fine, but the challenge is always data processing. And in the setting of cardiac imaging, unlike neuroimaging, we have to deal with mechanical noise, in this case, irregular periodicity of the cardiac contraction. People doing imaging realize how challenging to address MRI images in a setting of atrial fibrillation. Likewise, so we have to incorporate synchronization algorithm in collaboration with my collaborator, Professor Jie Ku at USC. So this collaboration resulted in this type of well-defined left atrium and left ventricle, providing a basis for structure and function. As yesterday we heard about in silo and simulation. Likewise, this type of simulation process is essential for precise computation of fluid dynamics. And along with this advancement in spatial and temporal resolution is the possibility to study neural crest-derived migration. We heard about this yesterday, about SOX10 migration to give rise to the first half field and second half field. And people know in this field that any ablation to this migratory pathway could be the basis of congenital heart disease, such as Notch mutation giving rise to cardiomyopathy, as reported by Epstein and recently Yost, and further demonstrate that mutation in Notch signaling could be the basis to cardiomyopathy. So by using this three-dimensional approach, now this one can label the neural crest subpopulation with SOX10 in this way, and the CML light chain in green fluorescent. So this three-dimensional time lapse provide a basis to generate the migration of neural crest cell at 26 hours and probably can even up to 30 hours. And this data could be confirmed by confocal microscopy showing presence of SOX10 label subpopulation of cardio neural crest cell at different hours after fertilization from 30 up to, I think it was up to 70 hours, and showing different distribution. Since we heard about this heterogeneity of cardiomyocyte, heterogeneity of fibroblasts yesterday, I think this provides a basis to understand this differential responses to injury and repair. And furthermore, it provides the basis for us to study outflow tract formation. And in this case, this is the AV valve labeled with FLIC1 and GFP. and then cardiomyocyte light chain in disarray. So this basis is really the foundation for us to test the hypothesis, a simple mechanotransduction hypothesis that mechanical shear stress is the underlying mechanism leading to notch activation, thereby promoting differentiation, proliferation, or trabeculation. So this is the baseline and illustrating these trabecular ridges and at about 100 hours after fertilization. So if you could genetically manipulate the fish by GATA1 morpholino to reduce viscosity, thereby shear stress, so that reduction in shear forces attenuates the presence of trabeculation. In parallel, one can also inhibit contractility by introducing TNNT2 morpholino to generate this attenuated endocardial trabeculation. So this provides the basis to test the hypothesis that shear forces over time is implicated in this trabecular formation by way of this notch-mediated signal pathways, especially people talk about JAK2 and notch1B leading to upregulation of ERBB2. So this type of gain of function and loss of function analysis could be possible by combining both zebrafish genetics and light chain microscopy to test this pathway, and thereby providing the basis as to why we need to have trabeculation. And one of the mechanical bases is to provide this myocardial contractile function in response to injury. So we talk about zebrafish, so one can sedate the fish with Trican, or you can immobilize the fish with low male agarose, so that you can visualize the fish in this tubing very well. I think familiar, and I think many people in this audience have done this to provide 4D light chain imaging, and the time-lapse imaging, and for us, we can perform 3D volumetric reconstruction and data computation. I think the next challenge is to move from fish to the mouse heart. So mouse heart, as I mentioned before, this is the opaque tissue, therefore limitation of photon penetration requires the chemical clearance, so that this what otherwise opaque specimen can be rendered translucent by way of chemical clearing. So Sean will talk about the new generation of optical clearance. There are many generation optical approaches, optical clearing approach, but there are three fundamental principles that remain the same, regardless which type of method you use. Number one, this method provides hydrogel embedding, thereby providing three-dimensional conformation to reserve the three-dimensional confrontation during these chemical processes. The goal is to remove light scattering material, especially lipids or hemoglobin, and thereby one can really optimize this refractive index to provide optimal visualization for 3D as well as the other modalities. So this data was actually performed in 2016. So as you can tell, the technology in collaboration Reza Al-Hardy's lab provide this translucent myocardium. I think nowadays we can do better with the new generation chemical clearing. But regardless, so in collaboration with Reza Ali, using his E17.5, you can now visualize the ultrastructure, otherwise difficult with the traditional micro-CD or micro-MRI. But I think I'd like to point out to you that this image is not perfect. Look at this optical striking, suggesting that the light penetration is still not deep enough. To address this issue, then we ask the question whether we can incorporate two sources of light illumination. So the dual illumination, and in order to achieve deeper light penetration for detection. So shown here is the optical pathway. So this laser light was produced by this illumination, followed by perpendicular detection, and a host of light sources provide the possibility to image fluorescently labeled tissue. Next question is to generate multi-scale imaging. So I think the idea is to really understand the fundamental principle of light sheets. So this light sheet is a Gaussian beam, and so this is the focal point where one can provide high spatial resolution. And so that focal region is defined as the light sheet length, and the thickness is defined by this omega naught. So based on this variation, this basis, to change the light sheet length, and one can perform multi-scale imaging from zebrafish embryo using a light sheet length of 5 micron to 18 micron for neonatal mouse hearts. So this is the rainbow heart from Razor's lab using dual illumination. So now you can appreciate the capacity to visualize the spatial distribution of fluorescent labeled protein.
So you got 1 minute left.
Okay, in collaboration with the Yibing Wen, now you can also visualize hypertrophic cardiomyopathy as well as distribution of potassium channels. And I think Reza talked about MSP cardiomyocyte mapping in relationship to PAC3. Okay, so I think you can get the idea. So this new technology provides multimodality for imaging different specimens. So in the interest of time, I'm going to skip, and also to show you another approach at the super resolution that was spearheaded by our postdoc. And I feel very humble that reviewers is actually sitting in this audience to the paper. But that method provides this type of possibility to further improve this raw data so one can give rise to, one can generate this type of super resolution, otherwise difficult. And this is just another example. And then I think I got to finish the talk by mentioning about big data. So you have beautiful images, 3D, temporal variation, but how do you address big data to generate this kind of images? Therefore, machine learning, so the idea is to generate registration and segmentation is essential for imaging. And I think in the interest of time, I'm going to skip, except to show that this could also be used in collaboration with Tatiana Segura, who was in our institution, but 2 years ago, she decided to join Nanette Bursak at Duke. But this is the idea where this type of interaction can be possible for quantitative quantification, showing the interaction of dermal cell fibroblasts in relationship to microbeads as a basis of promoting stem cellness or stem cell proliferation. I think I just want to show it last minute. So this also provides you a means after this machine learning to embark on a journey into the zebrafish atrium, and then through the valve, so one can measure the valve area. And then the further journey allows us to explore the endocardial ventricular muscular ridges. Okay, and I'm going to skip this part. So at the end, so this talk really provides you with some fundamental understanding of light sheet imaging, machine learning, and cardiomorphogenesis. In the interest of time, don't have time to deal with the basis of cardiomechanics. I'm going to skip all this theoretical basis, except to tell you that's the possibility to generate segmental deformation. I think in the era of myocardial heterogeneities, it will be important to be able to have segmental information about contractile function and in response to injury and repair. I think it's a humble journey for us, and I think I'm looking forward to learn from the audience as well. The current expertise is only good enough to visualize 4D images using light sheet imaging, as well as the requirement for synchronization algorithm. So I think the future for us, or maybe for this audience, is the ability to generate light fields so we can further bypass a synchronization algorithm to provide better temporal resolutions. So with that, I just want to summarize the strength of light sheet as a potential niche for cardiac morphogenesis and mechanics. And these are the faces who make this research possible, and collaborators who enrich our scientific and technical strength. And I'd like to thank the audience, especially the postdoc and PhD student. I think sometime when I'm sure as a PI, when papers and grants are rejected, we are up at 2 o'clock writing grants, and your energy and our innovation is really the source of light at the end of the tunnel. And thank you so much.
Thank you very much, Tzung. Does anyone have any burning questions they'd like to ask? I could quickly ask a question maybe on your clearing methods. And as you said, there's quite a few clearing methods out there, so CDB, iDisco, and Clarity. I was wondering if you have any knowledge or opinion on what works best with the heart specifically, because different tissues seem to react differently to these different
Sure,
clearing
I think
methods?
I feel very humble because this technology is moving rapidly. The one Xiang Wu used, it's actually perfect for myocardium because of thick tissues. But for other vasculature, I think other technology could be also possible.
Great, thank you. If you could just join me again in thanking Tzung.